All right, so for the most part, this unit is going to be pretty familiar and similar to units that we've done in the past. By that I mean a lot of stuff works exactly the same in rotational motion as it did in all of the linear stuff we've learned so far. But one of the important things we do have to learn is how to compare the rotational information and the linear information. So we'll start with a kind of simple problem. Let's imagine that a wheel of radius 0.318 rolls 4 meters down a hill. How many times did it rotate? So we're taking the linear terms, it moved 4 meters, and we're going to try and figure out what that is in angular or rotational terms, as in how many times did it rotate. The big issue here, and part of what's going to help us start to understand this, is realizing that while it went 4 meters down the hill, that basically means that we could imagine taking a 4 meter long string or whatever, and if we wrapped that around our object, we could figure out how many times it wraps around. That's also how many times that it would have rotated, because as it rolls down, each side of that wheel is coming in contact, and so after it rolls around once, it's moved some distance, and then twice, 3 times, and so on. So let's go back to our circumference formula first and foremost. When we talked about circumference earlier in the last video, we said circumference is equal to 2 pi times r. This equation is actually on your formula sheet, but it's under the geometry area, and so sometimes it gets overlooked. But it actually will do a lot of the heavy lifting for the rest of this unit. So one thing that we're going to realize is that circumference, this is a linear term. We measure it in meters. So that tells us, like in linear terms, how if we stretched out a circle, how long it would be. This 2 pi thing right here, this is actually an angular or a rotational term. It's how many radians a full circle is. So that's already measured in radians. And then it turns out that this radius right here, this is just our conversion factor. If we multiply our rotations by our radius, we can figure out how far we've gone in linear terms. So I'm going to translate this equation down into something that's more general than just for a single circle. Let's say instead that the linear distance x around a circle is equal to the total radians we've gone times r. So really we just translated this down, not into circumference, but this is basically any arc length, any distance around a circle. And then this theta right here is still our amount of rotation. So if we're only going halfway around, it would just be pi and so on. And then we're keeping r around. So we can use that to solve our problem right here. We have, let's see, we know that the radius is 0.318 meters. We know that the total distance, our x value, that's how many times around the circle, how many arc lengths, or how much an arc length, more than one circle, but works just the same. That works out to be 4 meters. So then we can just say x equals theta r, and if we're trying to figure out what theta is, we'll just do theta equals x over r, or 4 divided by 0.318. And the answer that we get from this, we get that theta equals 12.58 radians. But this question here didn't ask us how many radians it rotated. It asked how many times. That's really a question of revolutions. So if I want to figure out how many revolutions it is, recall that we found out in our last video that we can divide by 2 pi to figure out how many radians it is. I'm actually only going to divide by pi though, because I want to get it in units of pi. So if I divide 12.58 by pi, I get almost exactly 4 pi. I put the pi back in because that if I multiply 4 times pi, I go back to 12.8. So it's 4 pi radians. Oops. So that is how we convert from rotational or from linear to rotational. The easiest way to remember this is that the circle E stuff all go together. So the theta and the r, the kind of things that you would associate with a circle, those belong on one side of your equation. And then the linear one goes by itself. But this formula actually can do even more heavy lifting for us because we can start dividing it by time. If I take x over time, so x divided by time, that's equal to velocity. So if I divide this side also by time, I can say in linear terms, velocity is equal to theta over time, and theta over time is our angular velocity, so that's omega times r. And then finally, linear acceleration, if I divide it by time one more time, will be alpha times r. So this actually gives us a conversion factor for all of our rotational motion variables, turning them into linear. And you can see that the pattern holds every time. The circle-ish stuff, the omega, always goes with the radius, so they always go on the same side. Just a quick note on units. Omega is measured in radians per second. R is measured in meters. So if we multiply those together, we'd have meters times radians per second. And recall that velocity is measured in units of meters per second. So you can see that they don't quite equal each other. And that goes back to what I was saying in a previous video, that radians aren't a real unit. They're just a placeholder because it looks weird not putting something there. So it really, omega times r gives us meters per second because radians aren't a real unit. And same thing happens with acceleration and alpha times r. Alpha is radians per second. R is in meters. So again, we would just end up getting meters per second, just like we have for acceleration. Okay, the last thing that I need to talk about is what is different. And this is a key difference between linear and rotational motion. We get this stuff if we look at two different systems. So let's compare the linear velocity and the angular velocity of this wheel first. So over here, if I'm looking at VA versus VB, and I'm looking at angular velocity, omega A and omega B, the rotation or the angular velocity would be exactly the same for both of them. By the time B makes one full circle, one full rotation, 2 pi radians, whatever, B has also made 2 pi radians. So every time that one of them makes this, goes however many degrees or however many, whatever angular displacement, the other one has to be the exact same thing because they're on the same wheel. So the angular velocity is always the same. I want to repeat, the angular velocity is the same. Angular is the same if we're on the same wheel. But if we're on the same wheel, the linear velocity isn't necessarily the same. You can see that even though they've made the same amount of degree change or amount of radians in that same period of time, A has gone a much greater distance than B has. So for the velocity for the one that's further out will always be greater than the one that's further in. You can imagine if we had another point, C right there in the middle, C would have almost no linear velocity, and actually 0 if it was right in the middle. Going over to the gears, though, if we try and do the same comparison with two gears that are in contact with each other, I have B on the outside of a gear and A on the outside of my gear. Omega A, omega B. A and B would have the same linear velocity. Because they're both on the outside of these gears, basically, unless the gears are grinding past each other so that they're like slipping and not doing what they're supposed to, if the gears are functioning as they should be, no matter what the size difference is between them, A and B should rotate with the same linear velocity right at the outside. But you can see that A is a much bigger circle than B is. So by the time that B or A has made one full circle, it's possible that B has made something like 2 circles. So the angular velocity for B would be greater than the angular velocity for A. So that's a conceptual idea, or this relationship between linear and angular velocities. That's something that they test on pretty frequently. So make sure that you're comfortable with that last piece that I talked about. So that's pretty much all of the linear versus rotational motion stuff that you'll need to know. Thank you for watching.